So in this slide deck, you will see two problem statements. The first one, you can take it as like a homework or exploratory thing, probably which may not get evaluated, which is about essentially analyzing tweets posted by football fans all over the world before NFL tournament happened. Okay, and then it's essentially like a document processing that we learned during, I think, in the context after we learned about k-means, right? Where we computed TF-IDF scores, and using TF-IDF vectors, we can do clustering, we can do some searching through the text and stuff like that. Okay, but the actual project would be, so okay, in order to do that, there are a bunch of steps you can go through, clean the data. We have already done all these things, transform text into numeric matrix, which is TF-IDF vectors, and then grouping similar tweets by clustering and stuff like that, okay? And the actual project that I would like to assign to you is building classification models on this particular Titanic data set. Okay. Before we get into the details of the project, let me tell you what is my goal in this project. Okay. My goal in this particular project is to kind of familiarize you all about the typical process a data scientist go through in working on real world problem. Okay, so the goal is not to work on like massive data, try to run it on a Amazon EC2 cluster to get parallel processing and stuff like that, which is more engineering, and probably you will get all that experience in a Hadoop class as opposed to a data science class. Okay. So instead of that, here the data is small. You can work on a single machine, or you can also run MapReduce using RMR and stuff, right? Nobody is stopping you from running MapReduce on a smaller data. Absolutely possible. That's your choice. But the goal is to kind of get yourself familiar with the entire process from starting to the ending. Okay, and I'll obviously tell you what the problem that we need to solve, and also the list of steps that we go through. Okay, I'll also give some code snippets in this slide deck that kind of help you kind of kickstart your project, and probably later on I will also post the sample solution as well, but I would really like you to try it first before you look at the solution. Okay, so that's the goal of the project. Okay, and the specific data set that we are going to work with is this Titanic data set. We all know the tragedy about Titanic. The ship sank on April 15, 1912. A bunch of people died, bunch of people survived. And the primary reason for a lot of deaths in that particular accident is that there are not enough lifeboats available for the passengers. Okay, so they had to kind of prioritize and do whatever they need to do in order to send people on those lifeboats. Okay, and those typical priorities are women and children are given more priority than men. For example, if you have a child, then if there is a child, the child has higher probability to survive than a male adult, for example. Okay, and also upper class people are given more priority than lower class people and stuff like that, right? These are all some hypotheses. Nobody knows what happened there. or probably some people know, but I don't know what happened there in actuality, but we can kind of guess what all happened, right? Now, so the goal of the machine learning goal is basically to predict which passengers are likely to survive in this particular tragedy. Okay, the data set we are going to see will have the complete information about individual passengers on this Titanic ship, okay, including their age, their profession, their gender, and all the other details, like which class of the passenger he is, whether it's first class, second class, all those things. And based on all this information, you have to build a classification model which predicts between two classes, survived or not survived, okay? And obviously, in order to do that, we have to create a data set with multiple features in it. There are already some features given to you, like age and gender, but you can also create new features which incorporate the type of hypothesis that we came up, right? If a person is child, then he has more likelihood to survive than others. And if he's an upper class person, then he's again likely to survive more than others, and so on, right? We can incorporate these kind of hypotheses by adding new features, okay? So we are going to see all that later, but the goal is to basically build a classification model that can predict whether a particular passenger will survive or not, okay? Is that clear? The goal of the project? So these are different variables that are present in the data. So obviously, in order to build a classification model, you need some ground truth, right, with some label information, okay? And the survival is essentially the label column. 0 means that passenger is not survived. 1 means that passenger is survived, okay? And then P class is a passenger class, first class, second class, third class, and the name of the person, sex, gender of the person, age of the person, oops, and number of siblings or spouses aboard on the, oops, I'm sorry, number of siblings aboard, okay, and number of parents aboard, number of parents and children for each passenger. And these two is obviously numeric values, and the ticket number, which probably doesn't add anything to a classification model, but it's there, unless you know some naming convention of the ticket number. But for our purposes, probably ticket number will not serve any add any new information, okay? And the fare of the ticket, and the cabin in which that person is traveling, and the place of embarked, okay? At what place they got onto the ship, okay? So these are the different variables that are present in the data. And you can always add new features into the data and create more and more robust and more richer set of features. Okay, that's the primary task of a data scientist. Okay, you were given a data set with some attributes, but based on your understanding, like we have one understanding that, okay, child is likely to survive more than other, okay? How can you kind of incorporate this thought into the machine learning model? And the best way is to create a feature that kind of indicate whether a particular person is child or not, and then use that feature in your classification model, okay? So that's basically you're incorporating some of the hypotheses that you're thinking about as new features in the data set, okay? And then you run your classification model and see whether, oh, this feature is really important or not. Remember, back in the days when we learned about naive Bayes or random forests or decision trees, there is some notion of variable importance, right? Which indicates whether a particular feature is important or not. And you can kind of evaluate that through that mechanism. So whenever I add a new feature, I can run my classification model. Obviously, I'll see the accuracies and other performance metrics, but also I can see what is the variable importance for that new variable that I added. If it's really important, then I'll keep it. If it's not really adding anything, I'll remove it and think about something else. Okay? So there's some more information about individual variables. P-class, passenger class is a proxy for socio-economic status of that particular passenger. First means upper class, second means middle class, third means lower class. Age is specified in years. And then with respect to family relation, there's a bunch of other information, what is considered a sibling and how that information is encoded and other things. Okay, you can read through that information. But the goal is essentially you have this data set with these columns, and survival is your dependent variable and all the others are independent variables. And now you need to create classification model. Okay. Now let's see what all are things we can do. Okay. First thing any data scientist should do on a given data is simply to do some data exploration. Okay. And in this particular data exploration phase, you are simply understanding what the data is. What are the characteristics of data? If you have a numeric column, you want to understand what is the distribution of the data. If you have a categorical column, again, you want to understand how many records are there in each category. Okay, is there a particular category more popular than the other? And what is the relationship between these individual categories with the corresponding class label? Okay, these are the things you want to understand. Again, if you have a continuous variable, then you want to see what is the mean value, what is the minimum value, what is the maximum value, whether the values are skewed or not. Okay, and this kind of exploration gives you little more insight into individual attributes, and subsequently you can kind of unknowingly apply this exploratory knowledge while interpreting the results of your model. Okay, and in this particular data set as well, you can think of a lot of exploratory tasks. Okay, and some of the examples I'm going to give here, but you can do a lot more things, and that's where the real project comes in. You can think of something new and then add it. That's always nice and encouraged. Okay, but some of the things that you can do is you can kind of plot the survival rate by the gender. Okay, because we have some understanding or some hypothesis saying that, oh, women are more likely to survive than men. Is it really true? Let's look at the data and understand if it is true. Okay. That's something you can do. And then similarly, what is the distribution of my age? How many children are there? How many adolescents are there? And so on. And similarly, distribution of the fare column, the ticket price. How many people paid more than others? Okay. This again has indirect, as we said, it kind of has some implications on socioeconomic status, which indirectly impacts the chance of survivalness. Okay. And similarly, you can plot the survival rate by passenger class to understand really if the passenger class has a role to play in predicting survival rate. Okay. So imagine I plot survival rate by each passenger's class. Okay, there are three classes: first class, second class, third class, and let's say it's equally distributed, meaning 33% of the people in first class, 33% of all the survived people are in first class, and 33% are in second class, 33% in third class. Okay, that means the survived people are equally distributed among all classes. Then do you think survival rate, do you think passing your class is really an important variable that you can use in your prediction? Probably not, right? It's not really discriminating the classes that I want to predict. Okay, since those values are equally distributed across all the classes, I cannot distinguish or discriminate between survival and not survival using passing your class attribute. Okay, in those cases, I will remove that variable from my model learning and I'll keep it aside. Okay, so these kind of exploratory steps will help you understand whether or not a particular variable will likely to become important in the modeling phase. Okay, so these are some of the basic things that you can do, but as I said, you can think of more tasks and do those. Okay, so that's about the data exploration part. Okay, and there are multiple ways you can do, like we have seen this function called table, right? I think we talked about this in the context of confusion matrix, where we constructed predicted versus actual values, right? And similarly, you can use table to kind of get the counts of survival rate across different genders. And similarly, you can do that for different ages, different passenger classes, and whatnot. Okay. This is some sample code to get the plot like this. And then here I can see this is an example plot, may not be the one that is reflecting the data because I don't think males survive more than females. Oh, no. Actually, this may be true. So one color represents survived and the other color represents not survived. And you can see the percentage of females that are survived and percentage of males that are survived. Okay. From here, you can kind of conclude that, oh, females have higher likelihood to survive. And then you will think about, okay, how would I incorporate this into my modeling phase? Okay. And you can do that similar plotting and stuff like that with other exploratory tasks that you think of as well. Okay. So that's the data exploration. And during data exploration, typically you also encounter problems with the data, right? Some of the data, some of the columns may be incomplete. Some of the columns may have some junk values or invalid values and stuff like that. So those are the problems typically present in any data set, because any real world data set. No real world data set is clean and nice and tidy. Typically they have a lot of issues with it in terms of format, in terms of the values, in terms of the correctness and so on, right? So those are the things that you will encounter during this data exploration phase, and then subsequently you will try to account for those problems in the data. Okay, that's your next phase of data cleaning and preparation. Okay, now that you explored and you have some knowledge about individual columns and you have knowledge about the different problems that the data has. Okay, if it has any problems, you can do some data cleaning. If you have any missing values, do you want to remove them or do you want to put a default value or whatnot? And if you have something junk values, you may remove them and so on, right? Depending on the problem, you will do something about it. Okay, and here in this particular example, data cleaning and preparation tasks include removing columns that you think are not useful. Okay, maybe the place where the passenger got onto the ship may not be important. Okay, that's just a guess. Or ticket number, right? Ticket number may not provide much information in order to predict whether a passenger will survive or not. Okay, those are the columns you can remove from your model and fix. Okay, and other most important data cleaning or data preparation task is a missing value imputation. Okay, so for whatever reasons, the real world data sets, you will see a lot of missing values. Maybe it's the error in data collection process or insufficient data and stuff like that. For whatever reason, there will be some missing values, and you need to deal with those missing values. Okay, and one common technique is to assume a default value for those missing values. Okay, like for example, in this data set, you will see some missing values for age. Okay, for some passengers, age is not specified. So in that case, what you would want to do, one thing you can do is simply remove that particular record from your analysis, which may not be encouraging because you are reducing your dataset size, and that may have some important details that you may be missing, right? Instead of that, you can assume some value to that particular record. And that assuming, for example, is simply you can take the average of all the ages, all the available age values, and you can assume that missing value to be that average. Okay, that's a standard way of imputing the missing value. Okay, that's the standard word, missing value imputation. That means you're trying to put some values into those missing values. Okay, that's missing value imputation. Okay, and other thing you can do is basically you can canonicalize based on the names. For example, if there's a doctor in the name, you put them all together. All the misters will be in one vector, all the misses will be another vector, and so on. Okay, and you can kind of put this information into your training data set. Okay, meaning, so typically if you have simply all the names, then those names may not be really useful in doing predictions, right? If my name is John Smith, do you think that will make any impact on my classification model? Probably not. John Smith or Doe Smith doesn't really matter, right? However, if I have Dr. John Smith and Mr. Doe Smith, that may have some impact. Since I have doctor as my salutation, maybe it means that that passenger belongs to a higher class and in terms of education or whatnot. And therefore, maybe there's a higher chance of survival. Okay, so that's kind of called as canonicalization, meaning it's like discretization in the numeric case. So remember discretization, where you have a continuous attribute, continuous values, and you are binning them into multiple buckets. Like for age, we did 3 buckets: less than 30, from 31 to 40, and greater than 40. Okay, so that's like canonicalization of a continuous attributes into 3 bins. And similarly, I can do canonicalization of my name column into 5 bins: master, miss, Mrs., Mr., and doctor. Okay, and I'm kind of adding that information into my training data set. Okay, instead of working with names, now I work with these individual values like master, miss, doctor, and so on. Okay, so after this step, my name attribute will have these 5 values as opposed to any random passenger name. Okay. Actually, so instead of creating, updating the name column, I can even create a new column with it. That's also possible. Okay. If you think both the name and this canonicalization helps, then I will want to have it as 2 columns. But since in my case name doesn't really matter, I just want to remove it and put this as a new column. Okay. And then similarly, I can do a lot of things, right? In order to do, so for example, we said whenever age is missing, we want to take average, right? And I can be a little more intelligent about it, right? So if the person has doctor and his age is missing, then I want to take the average of only those people who have doctor as a salutation. Okay, that means instead of taking a universal average and then using it for all the missing values, I'm being little more kind of intelligent in doing that. Okay, if a person with doctor salutation has a missing age value, then I'm replacing it with the average value among those doctors. Okay, that's kind of better than taking a simple universal average and replacing it, right? So that's exactly what I'm doing here. So once I divide it into individual groups here, masters, misses, doctors, and misters, I'm taking individual averages. Okay. So here, this particular statement computes the average age for all the people whose salutation is master. Okay. And similarly, I can do all the other things. And once I compute these averages, I can replace my missing values. And we have seen already in our missing values are represented by NA, right? So wherever there is a NA, I can replace it with the average value. So essentially, all these 3 steps is doing missing value imputation for age group. Age column. Okay. And you can actually see the impact of different techniques that you do. So this is one technique of missing value imputation. And the other technique that we talked about is simply take the universal average, that means average of all the passengers' age, and then use it as a common missing value imputation. Okay, and you can kind of do both and see how your ultimate classification model would look like in terms of performance, and see whether this particular intelligent way of missing value imputation will actually impact classification or performance. I don't know the answer. That you can find out by trying out different columns. Okay. So that's one, and this is a very, very common problem in practice, dealing with missing values. Any data that you take, it's 90% or more than that chance that it will have missing values, and you need to have some strategy of handling those missing values. Okay. And there are a lot of other things, like some of you already pointed out, you can add new variables or features into the data. Okay, like here I can add a new variable called isChild, okay, which tells you whether yes and no, whether that particular passenger is child or not, and what is the family size of that particular person. Okay, that also may be important, right? If a passenger is solo, then probably he may not have, probably his likelihood to survive is lesser than a person with a bigger family. Okay, that's just a guess, but that you can evaluate by adding a new column with that information and then seeing whether that makes any difference in your classification or not. Okay, whether a particular passenger is a mother or not. Okay, that you can get information from these things, right? number of siblings and spouses, number of parents or children, and the gender of the passenger. With that, you can kind of derive whether a particular passenger is a mother or not. And again, the intuition there is if you are a mother, then you have probably higher likelihood to survive. Okay, so creating new variables is all about incorporating your thoughts about the problem into the classification model. Okay, and you can think of several other variables that you may would like to add. Okay, and whenever you want to see whether that particular variable is really important, as we talked about, we can look at variable importance as given by random forests and decision trees, or you can simply see whether or not your classification performance is improving with and without that column. Okay. And other data preparation tasks would include like discretizing a continuous attribute, like a fare column. The ticket price is a continuous attribute. You may want to bin it into like low, medium, high, or whatever bins that you think of. Okay. Like here, I already have some clues about how to do that. Like here, I'm creating a new column, fare 2. First, I put all the NA values in it, and then I'm saying whenever train fare is less than 10, I put some, I put less than 10 as a value, and 10 to 20, I put another value. So it's like the discretization of the fare column, and then I'm creating a new column called fare 2. Okay, so this is one type of discretization, but you may want to think about different things as well. Doesn't hurt. And obviously, you want to do same cleaning and these things on both testing and training data sets. Or other way to do is do all this cleaning and everything on the entire data set, and then split it into train and test sets. Okay. And as I say it in here, once you add your new variables, you can always again do your exploratory tasks that you did before, right? Let's say I added this discretized fare column, fare 2. Now I can see, I can use table function to figure out how the survival rate changes according to these fare classes. Okay, maybe less than 10 will have less survival rate than greater than 40. Okay, so on. Basically, you can do your data exploration again on these new variables. Okay, let's proceed further. And okay, with that information, now you are in a position to start building your models. Okay, and as we have seen before, the way to evaluate the classification performance is to compute this confusion matrix and other metrics like precision, recall, accuracy, F measure, and a lot of other things, right? So obviously you want to do that for every classifier model that you built, right? So here I'm just kind of wrapping that as a function so that you can simply call that function and get all the information. Okay, so here I'm computing, I'm creating a function called perf, okay, which given the predicted values and the actual values, it computes all this and returns. Okay, something like this. Okay, that's just for like reuse of my code. Okay, but you know exactly how to compute all this, computation of what is this called? Confusion matrix and true positives, false positives, and all the others, right? Now, the first model, the simplest model, can be to predict that everyone will belong to a majority class. Okay, so let's say I'll take all my data. Each data point has survived or not survived. I will look at how many people survived and how many people not survived. Okay, let's say the majority is not survived. Okay, just so let's say the majority class is not survived. Okay, the simplest classification model I can think of is that given any test record, I'll simply predict that it belongs to the majority class. That means it's not survived. And then I can see what is my classification performance would be. Okay, that's simplistic model. It doesn't use anything on the test features. It simply takes the test record and says it's survived or not survived, whatever is the majority class. Okay, that's your first model. Predict all test instances to be the majority class from the train set. Okay, now then you can see what so that means your predicted array will be that majority class, and the actual will always be coming from the test set, right? So then you can see what the performance of such a simplistic model would be, just to get your hands dirty. Okay. Okay, now that's a very simplistic model without really using any independent variables, but obviously you can do a lot more. One way is to create a model based on gender-wise survival rate. Okay, so for example, we already looked at in the data exploration phase, we saw that females are more likely to survive than males, right? So how can I incorporate that thing into my my classification model? Essentially, whenever there's a female in my test record, I'll say that person is survived. Whereas whenever I have a male in my test record, then I'll say not survived. Okay, and then I'll see what is the classification performance. That's exactly what I'm doing here. It's just basically looking at the distribution of male and female in the training data. Okay, and as you see, you are learning some new functions as well, like prop.table, which is essentially proportions, like percentages as opposed to simple counts. Okay. And then similarly, you can check if accounting for child and other new columns helps or not. Okay, I can create more columns about child and other new columns that I added, and then create classification models based on that as well. Okay. And for each of this model, I can kind of see what the classification performance is. And then, so as you can see here, for these simple models, I'm not really using any like a random forest or a decision tree or anything. The models are much simpler here. It's not really any mathematical model that we are building. Simply by seeing whether a particular person is child or not, we are saying he's survived or not. And simply by looking at their fair class, we are saying that person is survived or not. Okay, that's also a classifier model. It's just that it does not depend on any underlying mathematical model. Okay, those are simple, simplistic classification models. Okay, and you can kind of evaluate what the performance of those models will be. Okay, and obviously the more complex things that you can do is build the actual models that we learned, like naive-based classifier, decision trees, random forests, and so on. Okay, and so the first thing you can do is build a decision tree, and here again you have choice of choosing what attributes, what independent variables that you would like to consider. Okay, remember while creating decision tree, you need to provide a formula which says like survival is a function or function of some independent variables, right? There, if you put a dot in the formula, then you are taking all the columns. Or if you can provide individual columns, you can provide that by using plus, right? So that you can play with. And then you can also play with the R part control parameter, if you remember, which kind of governs when to stop, what is the size of the leaf node, how the class for the leaf node should be chosen, and stuff like that. Okay? And then as you play with different things, you can keep evaluating your performance of the resulting classification model so that you can kind of see how your changes to the model are impacting the ultimate performance. Okay? And that's why I kind of created this function so that you can simply call that function and get all the values. And then obviously you can build a random forest, you can also do naive-based classifier and so on, right? So far you can you build some simpler models and you build more complex models like decision trees and random forests and naive-based. I did not specify naive-based here, but you can absolutely try that as well. Okay, and the other thing that you can try, which we did not cover, is something called logistic regression. Okay, this is yet another classification model. Actually, before I go into, so since we did not cover it, I actually gave you the code as well to see how it looks like. But before we look at the code, let's try to understand what is this regression, whether it's linear regression or also logistic regression. Okay, so in a very, very simplistic terms, linear regression is essentially you have a column, you have a target column, which is your dependent variable or the predicted variable, and you want to model that dependent variable as a linear combination of independent variables. Okay, so it will look something like this. Your y is the dependent variable, your label column, okay, and you're modeling that label column as a linear combination of all the other columns, which are xi's. Okay, so here betas are some coefficients that you want to learn. Okay, individual coefficients, and then you're modeling this dependent variable as a linear combination of independent variables. Okay, and linear regression will try to find out what these betas are. Okay, so it's like fitting a line. I'll show you some examples if you would like later on, but it's like fitting a line over a different set of points. And typically linear regression is used whenever the dependent variable is a continuous attribute. Okay, if you want to predict the temperature, if you want to predict the humidity levels, if you want to predict the height of a person. Okay, so all these things are continuous attributes, right? And in those cases, you would use a linear regression, and that's why it's called regression. Okay, and in case of logistic regression, you don't consider your target as a linear combination. Instead, you consider it as a logit function, which would look something like this. So instead of simply linear combination, I would think of yi as 1 over 1 plus e power minus of all this. Okay, And then I can model this way, and then I can run my logistic regression and then compute individual betas. Okay, which will kind of gives you some probability value, which is again a continuous attribute, and that's why it's called regression. But you can use that logistic regression to do classification as well, since it's a probability value. So remember, we talked about as we predict, we can specify type equal to class, type equal to probability, and so on, right? If it's class, it will simply tell you whether it's positive or a negative. If it's type equal to prob, then it gives you the probability that it belongs to positive class, probability that it belongs to negative class. Okay? And logistic regression gives you the probability. Okay? This is the one that it gives. And you can say that, okay, whenever my probability is greater than 0.75, I will say that is a positive example. And whenever the probability is less than 0.75, I'll say it's a negative example. Or some other thing, 0.6, 0.8, doesn't matter, some threshold. Okay, so even though it's a regression, you can use it for classification. And in this example, we are essentially doing that. And logistic regression in R can be done using this function called GLM, generalized linear model. And just like decision trees, it takes equation. Survived is a function of all these values, okay? And with these extra parameters, it can do logistic regression. And it computes the probabilities, okay? Once you compute the model, just like you did predict for decision trees and other things, you can do predict.glm here, which will give you the probability. And here I'm writing some code which converts this that probability into survive versus not survive. And here I'm simply saying if the probability is greater than 0.5, I'll say 1, class 1, otherwise class 0. And then I can run this auth command to see what is the performance of my logistic regression function. Okay, and obviously you can play with the equation here, play with the threshold here, and so on, right? That's a very quick and dirty discussion of logistic regression. So this is something that you can do apart from the classification models that you learned in this class. Okay, so essentially, so far we have done data exploration just to understand what the data is, and then data preparation and cleaning to kind of add new columns or to clean up the existing columns. And then we played with some simple models, like taking the majority class or based on gender, based on child or not, and stuff like that. And then we also did more complex models like decision trees, random forests, naive-based, logistic regression, and so on. Okay, so with all this, you can kind of see, and then for each of those models, you will predict. You will look at the performance, how it performs on one test data, and even you can go further, and then you can do cross-validation, where you construct multiple train and test splits, and then take the average across all those individual splits. Okay, I don't know if you remember cross-validation back from class 5 or something. But you can look back on that and then do cross-validation as well, which would be even a nice way to kind of conclude the project. Okay, and finally, you can kind of write out the type of model that you tried, what is the performance that you got, and what are your conclusions about that particular model or a particular attribute, particular variable, whatever thing that you can kind of conclude from your analysis, okay, that you can kind of provide and provide in your report. Okay, I think that would be the overall goal of your project. So yeah, with this thing, I hope you will get complete like an end-to-end experience of a data science scenario. Okay. So the best way to get the support for the project would be to contact Edureka support, and because they already kind of already answered questions for a lot of people, and they may have a quick turnaround time. And if whenever they cannot answer, they'll come back to me to intervene. So best way to get support for the project would be to start from Edureka support, and they're 24/7. So whenever you send an email, there'll be some person who will be reading that email almost immediately. So your turnaround time would also be less. So the reference material, yeah, that's again, you would see it on LMS already under module 10, the further reading. Some textbooks, I think we already seen some of this in the beginning of the class somewhere, but anyway, you can get all the information here always. So the first one, Tom Mitchell book, is like the Bible for machine learning. At least I consider it as Bible. And then some popular data mining book. Again, as somebody pointed out, there's gray area between data mining and machine learning, so there'll be a lot of concepts covered in both the books, and a couple of other good books as a reference material for your library. Okay, and some pointers online, some video lectures. I think somebody asked about what other classes you can take, like Coursera class on machine learning, and some old videos that's already there by this Professor Andrew Ng, who's, I think, popular in Coursera. And then other video lectures on core machine learning techniques. But all of these are kind of deep mathematics stuff. Okay, and some blogs, or not really blogs, but kind of news websites. KD Nuggets, Datanami, and Kaggle. Kaggle is very interesting. You can enroll into challenges, machine learning challenges, and solve those problems. And if you are a leader on the board, you will get some prize. So this is like Netflix challenge, but posted by many companies. And it's real. Real meaning real companies post their problems, and actually, I heard companies like Facebook and other companies, they actually hire some people through these processes. So they post a challenge on Kaggle, and everyone tries the solution, and whoever is the winner or top few winners, they will contact for possible opportunities and stuff like that. So it's a very good website to start exploring some real data sets. Okay, and also we talked about UCI data repository, where you will see a lot of data sets for classification, clustering, and blah blah blah. There are many other data sets, and then we again, I think, talked about linear algebra lectures. If you want to learn more about it, this is an excellent source of information. Okay, that's some online pointers. Okay, and some resources related to R. Yeah, I think that's about it.